So folks, Alex here. So if you remember, in one of my previous videos, we did tackle the MD5sum implementation in Rust, and I was just curious like how hard that would actually be to kind of implement that algorithm at all, and how hard that would be to be, somewhat similar performance-wise to what we have in core utils. And it turns out to be pretty easy, to be honest, right? So the algorithm itself is, pretty straightforward, and I did, some basic optimizations, maybe like unrolled some loops and stuff. And yeah, my implementation was around like 5% slower than the core utils one, which I think is a W, because like core utils one literally received like decades of optimizations and whatnot, and I think that's fine. So I don't want to compete with that, although I could have, right? So then I tried to re-implement the sha256 actually, but that was kind of underwhelming as well, right? Because it uses the same Merkle-Damgard construction as MD5, although the compression function f is different, right? And the overall structure, including the the block size, which is 64 bytes, is the same. The output size, is larger. So for sha256 is of course 256 bits long, but otherwise, it's kind of the same, right? So I did implement that, and actually turns out to be pretty much the same as MD5, right? And cargo test. So the tests pass. We can build release, and we can, I don't know, like target, release, sha-la-la-la data. Let's actually do time it. Okay, so it's this, and then that would be sha256 sum, right? And that would be like what? That would be slightly slower even, right? So our implementation is even slightly, no, wait. No, our implementation is slower. But like this actually depends on kind of the state of the machine, right? So the like how warm the file system cache and whatnot. Because like I did have runs where mine was like several percent faster than the core utils one, and vice versa. So it's really kind of, I would say we've reached the place where we are on par on the kind of industry standard, right? So the reason today's video exists is that we will try to go ahead and speed up that implementation even further, and the way of doing that is that we will be using something known as vendor intrinsics in CPU. So basically, like at some point, Intel and some other vendors decided that it would have been fun and productive to add a bunch of new instructions specifically to compute sha256 faster, right? And we will see like what these are doing and stuff. But looks like sha256 is like modern enough and kind of important enough to actually be implemented like directly in silica, right? So the thing is that those instructions actually operate on XMM registers, so on SSE era SIMD registers, 128-bit long, right? So that would kind of, like that thing alone would kind of make us to consider using SIMD for the rest of our code as well, right? And in order to understand how to rewrite our implementation using those intrinsics, we would need to understand like how the actual message works, how the actual hash works. So it says for I from 1 to n, basically like for every block, every like 64-byte block of your original message, right? You would do this. So step 1, prepare the message schedule W. So the message schedule is basically a, your message block, but extended, right? So MD5 actually worked on those blocks directly, but sha256, they decided that it would have been great to kind of extend your block into some kind of, local buffer, right? And then, in such a way that your block is actually a prefix of that schedule W, right? And then just use whatever that is, right? Whatever like that data is, to just extend that all the way to the end. And I believe like the rationale here would be that, that would like introduce more entropy and more randomness to that whole process. And the ultimate goal of the hash function is to produce randomness, right? You need to produce kind of white noise, but in such a way that that white noise is like tightly coupled to the original message. That's basically what hashes do, right? So then initialize your state, right? This state is 256-bit long. And basically just compute the actual hash function, like whatever this is, right? I don't even care. And then that computation actually like changes the state, and you would take your local state and you would concatenate it, but not concatenate, but like add up with the state that you've accumulated so far. And for the last block, that would be your output, right? So that's that. And like what parts of that algorithm actually being sped up using the hardware tricks. So it turns out that like that part was sped up, so the kind of message extension part. So specifically like that computation, they have implemented it as this sha256 message 1 instruction, right? So it does this, it does sigma 0 W4 plus W3 and whatnot, and this is exactly what that thing asks for, right? If like when you unroll that loop, you would see that, right? Then you would need to add these two together just using whatever SIMD operation you have on hands, right? And then that part is actually implemented in hardware as well, right? So that would be message 2 thingy. So sigma 1 from something something, and it would be, what is it? It would be that part, right? And then you would just add these two together, add these two results together, and you would push that into your schedule, and thus you would speed up your schedule construction, right? And then for this, actually, they have implemented that whole round completely, right? So it turns out that this round 2 thingy would basically produce 2 rounds of sha256 operation for you, right? Like that whole abomination over there, right? B signature 1, ch of EFG, whatever this is, that all been put in there. So which is a which are great news actually for us, right? Although what's not necessarily as great is that like look here, right? So we kind of have this nice naming for our state variables, right? From A to H, right? But here, the way it works, it would actually, like the way that round computation works, it would actually take A and B, which are in turn like, A actually contains the state variables C, T, G, and H, and B would contain A, B, E, and F, which can blow your mind maybe a little bit. So we will be needing to like do a nice remapping between those things in order to make it all work. But yeah, otherwise the algorithm is still pretty straightforward. Hopefully it will get even more straightforward in SIMD. But we'll see. So yeah, let's just go ahead and delete all that. So okay, let's start. So prepare your message schedule. So let's see, let mute schedule is what, right? So, you know, prefix your schedule with your message, right? And here they kind of imply that the message, that the schedule and the message is basically an array of U32 numbers. But we are not working with U32. We will be working with SIMD values, right? So use std arch x86, and we will import everything for now. So let's go ahead and load 128. Let's see, load unaligned, right? And it would take a const pointer to this SIMD register thingy, right? So what is this? So we would take our chunk as const pointer to U8, and you know that it's U8. Please know that it's U8, dear compiler. So we would add 0 to this, and yeah, what else? As const pointer to am this, right? So that should be our first value. This operation is unsafe. I wonder why. Yeah. And add is not happy, so type annotation is needed. Okay. Why don't you know that it's U8? You're supposed to know that. Okay. Cool. But that's even not it, right? Because like when you load your stuff from the chunk, we actually need stuff to be in big endian, but when you load it from your chunk, it's little endian. So we'll be needing to shuffle. So shuffle ap la la la, and shuffle basically takes your thing that you need to shuffle and takes a mask that is used for shuffling. So we'll take this, like, right, and then the shuffling mask would be set API this. Okay, so again, we are working with 16 bytes, right, at a time, but in actuality that would be like 4 32-bit long numbers, and each of which we need to turn into big endian. So it will be like 13, 14, 15, and then 8, 9, 10, and then 11, and then 4, 5, 6, 7, right? And then 0, 1, 2, 3, right? Like that. So that would be our first thing, right? From here. So we need this, we need that, and let's just go ahead and copy that several times. So this is from shift 0, shift 16, right? Shift 32 and 48, right? Cool. And the rest of that schedule should be just zeros for now. So that would be 0, 128, right? And we need many of these. Okay, so what is the LAN? 15. And the current LAN is 16. Cool. Cool. So at that point, we're supposed to have this schedule pre-configured, right? Which means that, yeah, that part is done. Then we need to do this thing, right? Now we will be using the message 1 and message 2 thingies. So for extend round in for 216, right? So let's let's try to compute that part, right? So that would be like sha256 message, sha256 message 1, and these would be like schedule extend round -4 and schedule extend round -3, I think. Around -3, right? And that would be our mute TMP. Cool. So we have this, and basically we have kind of that part, right? Let's just copy that over, or otherwise I'll just lose my mind. Okay, so this, right? So let's call the next thing W7 then. W7, that would be so in order to get W7, basically like several values, we need to look up values on the border of two chunks and shift, right? So that would be like align APR with the schedule extend round -1 and schedule, what is it, like extend -2, and maybe like let's shift it 4 times, right? And then let's say we want to do that sum, right? So that would be like add AP 32 between TMP and W7, of course. And let's just finalize our schedule. So extend round is like sha256 message 2. Okay, and then here it will be like TMP, and here it will be schedule extend round -1. And that should do it, I think, right? So we've extended our schedule, right? And then initialize the working variables. Although, like, I'm not sure that this is correct, but we will see. Yeah, what's not nice about that state initialization is that, as I said, this thing says that A, B, C, D, and E, F, G are kinda go in sequence like this, but our actual round function is somewhat crazy, right? So it needs them to be in that order. C, D, G, F, which is, oh Jesus, from Intel, from, okay. Yeah, I think that's enough. Okay, so cool. So let's say let mute state 0. Let's say it's set AP32, and that would be H0, H1, H4. And then H5. So these supposed to go kind of in the reverse direction, but actually the signature of that function is fucked up as well. So it takes its values like in reverse for whatever reason. So yeah, as I32, right? So state 0, what about state 1? Kind of the same thing, right? So that would be like 2, 3, yeah, like 6, right? And then 7, right? Right, so, and of course we will be needing like to save whatever we have right now, because like at the end we will be needing to add these together, right? So yeah, let's do this. So I wanna call it like state 0 save, state 0, and state 1 save, state 1, something like that. Yeah, and we basically did these 2 steps, and then we need to compute the actual hash, right? So for SHA round in from 0 to 16, right? So the round index would be like SHA round times 4, because we are working with yeah, because like the you understand that, right? Because like we are the original implementation says that we need to work with U32, but we are working with I128, so it's like 4 times larger. So that's why times 4. And this is where the actual constants are coming into the into the place. So set I32. Right, what are these? So round index plus 3, k like round index plus 2, plus 1, and yeah, so index plus 1. And what's here? It's like k round index as is, right? Oops. And yeah, as I32, 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 I32. So these are constants, right? And I don't know. So we have those constants, right? But then we somehow need to invoke the round function. Oh, let's yeah, like SHA round, and then state 1 will be just SHA256 round of state 1, state 0, and we will add let's see, that thing actually wants us to perform and B and pre-computed some of the next 2 rounds, right? So it takes A, B, and K, and the K here is supposed to be W rounds plus K constants, right? So AP 32 of W rounds and K constants, right? Like that. Cool. So state 1 and state 0, and of course like the actual sequence in which those states are passed are also kind of, you know, huge F to my face, because like A actually contains kind of the second part, not the first part, which is, I don't know. Yeah, state 0, state 1, right? And then we kind of need to this, and yeah, let's shift, right? So what is it? Let's see. Okay, so shift A right by that amount, right? So W rounds, let's shift it 8 times, like K consts with that, and like that, like that, like that. Is it? Yep. So yeah, basically now we've computed our state 0 as state 1. Now we can try to unwind, not unwind, but like try to add whatever we had before that, right? So so state 0 would be at AP32, right? Of state 0 to state 0 safe, and the same thing here, state 1, state 1, state 1 save, right? And now we are ready to bump our output values, right? So that would be extract AP32 from state 0, the value 3, and SU32. So let's see, we have a bunch, H1, H2, H3, H4, H5, H6, H7, and that's it, right? So state 0, 3, okay, then state 1, 3, oops, state 1, 2, state 0, so 3, 2, 3, 2, 1, 0, okay, so 1, state 0, 0, and then state 1, 1, and state 1, 0, and that whole thing is now unsafe as well, so unsafe, safe. Although I don't know, it maybe is safe. It's safe here. That's fine. Ooh, cargo test. And yeah, the tests still work. Yeah, and let's do cargo build release. Okay, so let's see. SHA256. Yeah, it's a second and a half, and our implementation is 390 milliseconds, which is, well, 4.5 times faster or something, right? Which is pretty good, I think. So yeah, I mean, that's that. Yeah, so the SIMD code and the kind of intrinsic code is pretty is pretty tricky to pull off, honestly. So, but you know, that's kind of the implementation that I came up with. You can actually do slightly better than that. Like for instance, here you don't need to extract those variables, you know, like that independently. You can just dump whatever a set of your SIMD registers, it's probably like you can like concatenate you know, several SIMD registers together and shuffle it, shift it a little bit, and then dump whatever left to memory. But yeah, that's beyond me. So that's, you know, the kind of implementation we have right now. Let's do hyperfine then. Let's do kind of a proper run for that. Okay. It's kind of slightly slower than I would anticipate it. Although, let's see what we have here. It's like open SSL, sha256. Because like OpenSSL's version basically does the same thing as mine. Is it any faster? No, it's pretty much exactly the same. Yeah. So yeah, I would say this is a W. The code itself, it doesn't necessarily seem to be that complex, but you know, figuring out all those kind of alignments and whatnot might actually be pretty daunting. So yeah, this is something to kind of be aware of. But yeah, that's that. So let me know if you have any questions, and that's that. I'll see you on the next one, and bye.